Okay, now it's working. I don't know. Okay, so first I'll just give a brief introduction to myself and the group and what we work on. So I'm actually maybe a very good candidate for bridging quantum and nano because I'm in the quantum nanoscience department at Delft University of Technology. Which is indeed, and we are together with the bio nanoscience department, as part of QTech, part of the Kavli Institute of Nanoscience in Delft. There's lots of institutes and lots of organizations that all overlap in some weird Venn diagram. But this is what it looks like. Sometimes it's sunny, then we take a picture. It's not always raining. So we have the sort of themes we've been trying to profile ourselves with, where we talk about quantum matter, and by that I mean we really need materials, but also quantum sensing and transduction. And my stuff sort of falls a little bit more in these lower categories. So also I'll say that we are in principle actually hiring as well. So we're looking for tenure track and possibly senior people. So if you know somebody who is interested in joining our institutes, we have a great clean room. We have a great collection of scientists working on topics in quantum and nano. So please have them contact us. So this is, I made this sketch a few years ago to sort of very busy sketch to sort of show a little bit what we work on in the group. I'd say the core of what we do is we make superconducting quantum circuits. These are little circuits made of superconductors on a chip that we make in the clean room. And then that is sort of unifies all the stuff we do. And then very broadly, we couple these superconducting circuits to mechanical oscillators. And I'll tell a little bit about that today. I will not tell about quantum gravity because those will be maybe in 2 or 3 years. You can invite me back and I'll tell you about quantum and gravity. And we also work, but we also play around in the playground of circuit QED, where putting, inductors and capacitors and Josephson junctions in funny ways on the chip, you can start to play around and explore funny regimes of quantum mechanics. So some examples of what these things actually look like. This is the thing I'll tell you about today a little bit. This is this beam that can vibrate up and down on the mechanical side. This here is actually a millimeter size membrane that can also shake. And that's the sort of object we want to start in the future, in the coming years, to try to really look at making quantum superpositions large enough to look at gravitational forces, let's say. And on the other side, we have been playing around with funny combinations of circuits for quantum radio frequency applications, and also putting them together in larger ways to make quantum circuits. But what I want to tell you about today is on this outline slide. So I want to start a little bit broadly talking about Josephson junctions and the way, what role they play in what I'll call superconducting quantum technology. This is the heart of the processors that Google and IBM have huge commercial efforts at making now. This has really gone in the past, say, 10 years, a transition from science into really quite significant industry. You can actually buy a quantum computer from IBM if you have enough money. So if you want one, you can just get a quote. But so I want to motivate this a little bit. Then I want to take a step back because it is quite a broad audience, and I want to try to explain as best I can to you at a very basic level what these circuits are and how they work. So I want to give you some sort of feeling and flavor for what's actually on this chip from IBM, and what are the components you need to put into them, and how does that how does that allow you to do quantum stuff. Then I'll tell about what I'm going to call strongly driven Josephson cavities. These are sort of a funny, different regime that people don't usually look at, and that's going to be the main part of the work, where I'll talk about weird physics that pops up when you strongly drive these things, how you can use this for strange cooling schemes, and what happens when you do even weirder stuff. So, wrong button. So, superconducting quantum technologies. So at sort of the heart of all of this, this sort of revolution is this guy here. It's called a Josephson junction. It's two pieces of metal that you stick together really close and you separate them by a small tunnel barrier. And classically, you would not allow, it's quantum mechanical tunneling. So classically, the electrons would not be able to get from superconductor 1 to 2. But in quantum mechanics, their wave function leaks out in a little tail. And so the Cooper pairs of your superconductor can actually make it through from one side to the other. That was actually the puzzle. This is the puzzle that people went out to solve and look at in the early 1960s. This is where Brian Josephson won his Nobel Prize for figuring out exactly what happens and discovering the fact that you can actually have the Cooper pairs tunnel through this thing, which would be in principle impenetrable classically. But then not only do that, but do that by carrying a supercurrent, which allows current to flow with no voltage. There are actually, if you do the math, which I won't do, you get the one thing which is kind of obvious. You get DC current with no voltage. But what's also kind of even a little bit weirder is you can also get, if you put a DC voltage, you actually get no current. So it's kind of a Jekyll and Hyde. If I put current, then I have no voltage. But if I put voltage, I have no current. Actually, you get an AC current when you put a DC voltage. That's actually the basis of really commercial technologies. For example, there's the current standard of voltage is based on an array of Josephson junctions that you, using an atomic clock, you can actually generate with an extremely high degree of precision a well-known voltage. And that is actually the basis of sort of the metrological standard of voltage that is used. And the other funny thing, this is all from olden days. This is sort of from the 1980s, the physics of the 1980s here. But if you take two Josephson junctions and put them in a circle, in a loop, it turns out you get something called a squid. And this guy is super, super sensitive to magnetic fields. If you make a squid that is even not that big, but even much smaller, on the order of a few microtesla or nanotesla, you will have a signal that goes from full resistance to zero resistance with a periodicity of nanotesla. And because you have this thing that's so incredibly sensitive to magnetic fields, it's actually even used commercially, despite the fact that you have to cool these things down to cryogenic temperatures. People do things like, if you go to the hospital, you can sit in this chair and they will have a whole bunch of squids that will be measuring the magnetic fields from the thoughts in your brain. This exists in hospitals. And also people do things like hang them off of helicopters and fly them around. And there they use the sensitivity of the squid to be able to detect a mass being pulled by the gravitational field of oil fields underneath the helicopter. And so these are very sensitive. But for me, this is what I'll colloquially call quantum 1.0 of Josephson junctions. And nowadays we're in sort of a new regime, what I'll call quantum 2.0. And quantum 2.0 has taken these junctions and put them, in quantum 2.0, these junctions form, for example, the basis of the superconducting qubit, which I'll explain a bit more in a bit. In this case, these are actually little harmonic oscillators with huge nonlinearity. That's actually how they work as a qubit. The other big application of these things in quantum 2.0 is for making quantum limited amplifiers. So this is a picture of a beautiful recent device where they can make an amplifier that can listen to microwave signals and add over a huge range of frequencies and amplify them with adding the minimum amount of noise allowed by quantum mechanics. This is now becoming sort of a commercial technology. And actually this one here is sort of, you make these like an amplifier, you want them to be linear, you try to make these, you do all the things you can to make them as linear as possible. And actually today, I want to talk about maybe what happens in between. So if it's a little bit nonlinear, but not too nonlinear, what happens? Is that useful? Can you do something? And that's what I called the Josephson resonator. So let's say, to give an overview of the stuff we've been doing in my group with Josephson resonators, in recent years, we looked at 3 different types of sensing with these. The first is actually, we've actually published a paper detecting current. It turns out that if I put a DC current through my Josephson junction resonator, then it changes its frequency. And this can be a very sensitive detector of the current levels. And this actually has potential applications in astronomical detectors, where people want to read out arrays of detectors, putting a small DC current out with very high sensitivity. And we think actually that this and future revisions of this could be an interesting candidate for that. So I'll tell you also, I won't talk about this today, but I will talk about nanomechanics. And that's where we use these Josephson resonators to detect the position of this beam. We call it ourselves, we call this flux mediated optomechanics. It's an old idea actually from about 2008, but it turns out it's really hard to do experimentally. And there have been many groups who have started and many groups just didn't finish it. And then actually in 2019, our group, along with 3 other groups, including the group of Hans here, but also Gerhard Kirchmeier and my former postdoc, who's now in Bangalore, all published almost simultaneously the first devices that were capable of this. And then there's a third type of sensing I'll tell you about today, which is kind of a funny, it's a bit a version of this. Sometimes I call it optomechanics without optics and without mechanics. But basically, it's a way we use the same type of principle of this device, where we have this Josephson resonator that can be tuned by flux, and then we make a inductor which couples flux from a radio frequency circuit into this object, and that we've christened, for better or worse, with the name photon pressure coupling, and now we can also use these to do quantum sensing and cooling and some interesting experiments with radio frequency photons. Okay, good. So the first but before I go into any of the details, I want to give a bit of a tutorial introduction into these circuits, how they work, how you can understand them at sort of at a basic level, let's say. So if I look at the chips that are made by Google and IBM right now, the building blocks of this superconducting quantum chip, there are 2 important elements. There's microwave photons, so this is like light in a cavity, and there are microwave artificial atoms. And then maybe I'll argue that someday maybe these Josephson resonators are useful or not. So and I want to take a bit of time to explain to you how we actually make those and what they look like and how they work. Oh, wrong button again. So for us, photons are easy. In principle, all I need to do to make a photon on my chip is I need to make an inductor and a capacitor. An inductor and a capacitor together make an electrical harmonic oscillator, which you may or may not be familiar with from your undergraduate quantum mechanics course. So this electrical harmonic oscillator, well, harmonic oscillators in general will have these quantized levels, which have these wibbles, these wave functions with wibbles. And the terminology, of course, is that we say that this resonator, if it's excited to, say, the 3rd state, we say that it has, if it's excited twice, we say that it has 2 photons. So these are a little bit different than, say, photons that we saw the other day on an optical table that are flying around and bouncing off of stuff. These are just kind of sitting there in the resonator. And how do we make them quantum? I mean, this guy here is pretty clearly not quantum. But how we make them quantum is actually relatively easy. We just make them really cold. So if we satisfy this criteria, that the thermal energy is much, much less than the level splitting, then in principle, our photons are quantum. And how do we do that? Well, I can buy from commercially a company a fridge that will go to 10 millikelvin. That's what I can buy. It costs 500,000 euro, but we just buy them. And then if I look at that, the thermal energy is around 230 megahertz in frequency units. So we just have to make this little LC circuit at frequencies in the gigahertz, typically around 5 gigahertz. And we just put it in the fridge, and it cools down, and he's cold, and he's quantum. This is what there's sort of two primary flavors of these resonators. One is to make sort of a transmission line, a coaxial cable that you fold out onto the chip. This will have, for example, a fundamental resonance at lambda over 4 in this case. And then we arrange that to be 5 gigahertz. And then that lambda over 4 mode will then be represented by this harmonic oscillator. Sometimes we also just make them literally by putting an inductor and a capacitor on the chip. We call these lumped element resonators. So so we have quantum photons, and then the question is, how do we make a quantum atom? You might be tempted to try to use your harmonic oscillator as a quantum atom. It has lots of levels, but I can say, okay, if I want my qubit, if I want to make a qubit of this, I could say, okay, well, 0 is 0 and 1 is 1. Yeah, that should work, right? It's a perfectly good qubit basis. And it is actually a perfectly good qubit basis. But the problem with that in practice is that it's really hard. And the reason is that when I think of a qubit like an atom or a spin, there's one property that makes it super useful. And that's that if I take my microwave generator, which is oscillating voltage, or if I take a laser, which is also just an oscillating voltage at a much higher frequency, and I shoot it at that atom or spin, then what happens is that I can stay inside of if I shoot it, let's say, if I start shooting it at the spin, then it goes up, right? But the nice thing about, say, a spin is that if I keep shooting longer, it goes back down. This is a Rabi cycle, Rabi oscillations. And that means that if I wait exactly the right amount of time, I can program anything I want. But the problem with these guys is if I just take this guy and start pushing him with my finger, shaking him, then he will start to go up. Some of his population will start to go down, but other parts of it will just keep going up. And so I will just run up this ladder. And it turns out that with a harmonic oscillator and just classical lasers and stuff, the only thing I can make are coherent, what we call in quantum mechanics, coherent states. These are just coherent oscillations of the currents and voltages in the circuit. And that is in some sense also the most classical quantum state that one can construct. So actually these are really bad. You can never make a superposition state using lasers and a harmonic oscillator. So what is the trick in atoms? The trick in atoms is that your potential is not harmonic. And that means that there's a different level spacing between, say, the first and second level, the ground state in the first level, and the first excited and second excited level. And that means if I shine my laser on this transition, I can undergo this Rabi oscillation. And the fact that I don't leak out up to the higher levels, that allows me to gain full quantum control in the Bloch sphere of my atom. So the upshot is that somehow to make an atom, we need something nonlinear inside of our circuit. So we need to go to the textbook of electrical circuits and find something nonlinear. You know, if you open up the textbook, probably the first thing you'll find is a diode. Turns out diodes are just not very useful in this case because they're dissipative. But there is a special magical item, which I've already introduced, which is this Josephson junction. And this Josephson junction has the advantage that it has zero dissipation. It makes it very attractive, so our excitations will last for a long time. And Mr. Josephson, what he won the Nobel Prize for were these two equations. And if you look at these equations a bit, you can do a bit of math. Turns out that if I put this guy here into my circuit, then the first order, this Josephson junction looks like an inductor. So most important thing is that if you see a little cross in that circuit, the first thing that should pop into your head, that's an inductor. And then we all automatically know what will happen to this circuit. It will look like an inductor capacitor, and it'll have some resonance. It's actually a super concentrated inductor. A Josephson junction that is 50 by 50 nanometers has the same inductance as like a 10 millimeter long piece of wire. So it's like a mega concentrated inductor. But that's not the only thing. It turns out if you look at these equations, because The inductor is, you get the inductor, by the way, out of these equations if I Taylor expand this sine function and keep the first term. But if I look at the higher order terms, it turns out, of course, you're going to get nonlinearities. That nonlinearity gives you a cosine potential, and that gives you exactly this difference in level spacing between the 0 and 1 and the 1 and 2. And that is something that allows you to start to make a qubit. And to give you sort of a feeling in the state of the art of technology right now, with this sort of, this is, by the way, called a transmon qubit. This fancy name, but it's basically just a Josephson junction and capacitor. And if you make a transmon qubit, you can get this difference of the levels to be like 300 megahertz. And because of the magic properties of these superconductors and junctions, I can still have a line width of that transition of 30 kilohertz. So I'm sort of 4 orders of magnitude resolved in the transitions up to the higher levels. And that's the whole basis of these guys. So this is what they actually look like in practice. How do you make a Josephson junction? There's lots of different ways to try. There's only one that really works in practice. That's using aluminum and aluminum oxide. So, and we have a little trick inside of the vacuum chamber. It's material science, and material science is messy. And the trick that people have found to make these things is that you put down, it's called it uses a trick called shadow evaporation. You can see there's 2 shadows. You make a single pattern, and then you deposit from one angle your aluminum, and then you have a stage in the evaporator that rotates around, so you can evaporate at another angle. And in between those 2 evaporations, you put a little teeny tiny bit of oxygen in the chamber, and that makes a tunnel barrier that a very controlled and very low loss tunnel barrier between this bottom piece of metal and this top piece of metal. And that's the Josephson junctions we work with today. Okay, good. So that's an overview of that's my superconducting quantum circuits 101. If anyone has questions, feel free to ask. So then I want to talk about, so now I'll shift gears and I'll start talking about a slightly different thing. So let's say maybe to give it these circuits with only the inductor are very, very linear. You could put like 10 to the 8 photons in them and they're still linear. These qubits down here, these are extremely nonlinear at the level of a single photon. That's the whole basis of a qubit. And what I'm going to talk about today is if you're somewhere in between. And that's what I've called Josephson cavities. And if you're a little bit in between, so a superconducting qubit, you can't really drive. If you drive it, it only goes up to 1 and back down to 0 and up to 1 and back down to 0. This is a Rabi cycle. So it doesn't really do much. If we have a weaker nonlinearity though, then we can drive it pretty hard. And now the question is what happens, and is that useful? And that's what I want to look at the first part of the talk. I don't even want to talk about sensing yet. I'm just going to say, let's take this weird thing, this weakly nonlinear thing, and let's drive it hard, and let's see what happens. And I've put the warning, because like the talk the other day, we will have some sharks. And but I'll guide you through the shark pit. So what is it? What do these devices look like? They actually are also not so different. They're a capacitor. In this case, we actually put a little bit of a geometric inductance in parallel with this capacitor. And we also have this Josephson inductance. And this Josephson inductance is actually a little bit of a different type of junction that has much weaker nonlinearity. And now, so that's the device. We've tuned all the circuit parameters so that it should have a resonance around 5 gigahertz. The experiment is pretty simple. We have a coaxial cable sticking onto this thing, and we send microwaves in, and we measure what reflects back out again. So if we take a look, first of all, it resonates. So we've done a decent job of our homework. We've designed this to have a resonance frequency around 5 gigahertz. And you can see that as we hit the resonance frequency of this thing, the reflection coefficient dips. And it has some line width that we've done a decent job of engineering. And now the question, first question, this is at very, very low power. So we're actually sub-photon average interrogation of the resonator. And you can ask, first question is what's going to happen if I turn up the power? So if I turn up the power, actually, that's the story of Germans and sharks. So this guy here is Georg Döffing. He was a German audio engineer in the 1800s, and he was the first one to really look at the response of resonators, where the force of is not just kx like we learn in undergraduate physics, but also with a higher order correction, in this case beta x cubed. And you can solve this. It's fun to solve. And what you see is that if beta equals 0, or at low powers, it just looks like a normal harmonic oscillator. But as I start to turn up the power, or the beta, then what happens is that you get this sort of starts to tilt. So if it's a negative beta, then it tilts downwards towards negative frequencies. And Josephson junctions always have a negative beta, actually. And if you turn up the power the other way, then he starts to tilt upwards. And where are the sharks? The sharks are that in experiments. So actually, you can see once this response curve folds over itself, there are 3 solutions, and 2 of them are stable, and 1 is metastable. So in experiments, we never see this dashed line. And what we do see, whether we see this bottom line or the up line, depends on which direction we sweep the frequency in from. Because which state you end up with in steady state depends on your initial condition in this nonlinear equation. And so in practice, what we see if we sweep the frequency is that we can, if we start from below, we follow this guy up, and then boom, when we hit the tip of this point, then we jump down. And then in our experimental data, we get these little shark fins. So this is the way that is parameterized in say classical mechanics. You talk about this nonlinear term with the x cubed. You can actually understand this a little bit pretty easily. Why does it shift up or down? If I look at sort of averaging over a cycle, then there's going to be the quadratic. You can sort of factor out an x squared term here from this beta x cubed. And that x squared term, when I average over a cycle, will have some non-zero cycle average. And you can, so you can then see that I'm going to change the spring constant. And that's sort of an intuitive way to understand how it's like a shift in the natural frequency that depends on power. So that natural frequency shift, it turns out, we usually parameterize that in terms, it's proportional to power, but power is like photons. And so we usually characterize that in terms of this number chi, and that's the number, that's the shift per photon. That's sort of the amount that the natural frequency shifts if I sort of oscillate it with the amplitude of a single photon of the 0-point fluctuation level. And actually there's a critical number of the point when you hit the point when you break, call it bifurcation, when this guy tilts so far that he breaks into 2 branches. That happens at what we call the critical photon number. And that's just, it's a very easy expression if you want to memorize it. It's just when the shift is equal to the line width. So when I shift this guy by the line width, then chaos breaks loose. Well, not mathematical chaos, but yeah. So, and actually what's a super fun thing is that the transmon qubit is actually a Duffing oscillator who's already bifurcated by quantum fluctuations, right? It's sort of the quantum fluctuations of the field on its own are enough to push the Duffing oscillator of the qubit into this bifurcation regime. I don't know what that means, but it sounds fun. Okay, so, but we're a weaker nonlinearity, so we have to drive hard. And indeed, if we drive hard, we see sharks. So as we expect, we have a Josephson junction, it's not linear. We're going to drive hard, we're going to get the sharks. But then we were just kind of doing experiments, because that's what we do. We started to ask the question, what if I put 2 signals in? So we're going to do this by sort of a pump probe measurement. So I'm going to drive this guy super hard. Well, I can change the power, but I'll drive it with one fixed frequency. And then I'm going to take another frequency and sweep through it. I see what I see. And actually, initially, this was not obvious to me what would happen. And then, so reminder, we're going to drive this guy, and we're going to pump this guy hard so that we're going to get to sharks, right? And now the question is, does the purple guy, does he see a shark or not? Well, what does he see? So it turns out we did this experiment, and actually the purple guy, he sees no shark. So this is the frequency of our pump, and we're changing the pump power here. And this is the probe that's going looking at what's happening. And it turns out that I can pump super hard. I can pump so hard that I would be in shark territory with no problem. But when I take this second tone and go and just poke it a little bit and feel what's going on, it turns out that this shows a completely linear harmonic oscillator response. And what's happening, what actually turns out that this harmonic oscillator response, the probe, he sees sort of a dressed frequency. He sees exactly this frequency I was talking about, that the natural frequency gets shifted by the fact that you're shaking it very hard with the pump. It's a bit like an AC Stark shift, but not mathematically the same, it turns out. I've learned recently. Actually, from this type of measurement, we can actually track this frequency as a function of the pump power. You can, by the way, you can already see that we're sharking, because this resonance is moving by much more than a line width. It's moving by like tens of line widths. So we know that this pump field is already in this bifurcation regime, but the probe field sees a linear response that's shifted and dressed. So actually from this data, we can fit this. Actually, this is exactly what I was saying. We can calibrate the power we provide into a photon number, and we can make a plot of the frequency shift as a function of the photon number. And as expected from Mr. Duffing, this is exactly a straight linear line. There is some funny stuff happening with our loss rates, but that's due to annoying technical details of real life in microwave domain. Dielectric losses are complicated. So then we can do another experiment. We can ask, so over here, I was sort of putting my pump on the blue side, we call it. And he was kind of safe over there, right? But we can also put this strong pump on the red side. And now what's happening is that this shark, he's tilting over towards us, right? And so he's gonna start attacking our pump. And now we also, so what will happen there? It turns out that that's something very interesting that we found. And so this is the same experiment, but now with the pump on this red side. What happens actually, you don't see it much here. It turns out this is just shifting just a little tiny bit. He's starting to tilt towards your pump. But there's at some point when the pump field jumps. Basically, the pump field goes from seeing this low branch, the bottom part of the shark, to the top part of the shark. And that means that you have a sudden jump from the pump field barely causing it to oscillate to oscillating really hard. And then the first thing that you can see is that this resonance here suddenly goes a big jump to the other side. And then he does what he was doing before. He just kind of walks away. That stuff that's kind of what you expect. But what surprised us the most was actually this guy. It turns out that when this happens, there was another line over here. And his line was exactly mirrored about this pump frequency. And what's also a little bit weird is that he's red, which means that the reflection coefficient is bigger than 1. Also kind of weird. Okay. What's going on? So we first put on our hats as microwave engineers and thought, okay, what is going on special over here that we somehow see this mirror copy of the resonance? And now the important thing is that our device is nonlinear, which means that like a mixer diode in your radio frequency receiver of your mobile phone or old school radio, it will generate, if you put 2 frequencies in, it will generate sum and difference frequencies. So what will happen, and actually this is known, this is common. And so what happens is that when I put this huge pump in here and I put my little probe over here, I will generate a mirror image of that probe on the other side. And it turns out this feature here, that's in the terminology of parametric amplifiers, this is called the idler mode, also from 4-wave mixing. And that idler, it turns out that this feature is associated with that idler coming into resonance with the shifted cavity response. So, and we call this internally from this perspective, call this idler resonance condition. So actually this other peak here is associated with this idler resonance. And it produces gain actually because of 4-wave mixing. So it turns out that we saw exactly this plot in Anya's plot the other day. So if you're a theorist, it turns out you know all of this. And you can actually solve what the susceptibility is of this driven Kerr oscillator. And you get exactly this. You get these 2, it turns out that you get these 2 quasi modes. I don't even know what to call them. We call them quasi modes. And as you turn up the photon number, they pull together. They reach an exceptional point, and then your cavity bifurcates and the photon number jumps over to the other side, and then they split again. And so this is sort of, you can look up, we looked this up in a paper that Mark Diekman has written loads of papers about this. And these modes are there in the math. And now what we've learned from our experiments is that you can actually see these modes directly in the spectroscopy because of this idler resonance condition. And this condition, of course, reveals to you in your reflection this second mode. How am I doing for time, actually? Not too good, okay. Okay, so part 1 summary is that in the strong driving regime, if you drive this guy really hard, you're gonna get sharks, but those sharks are with respect to your pump field only. And when you look again at the susceptibility for a second tone, actually, you get these extra quasi modes, which you can interpret in terms of idler resonance. Good. So then I'll go super quickly. Now I've established the basics. So the second thing I want to tell you about is what we call 4-wave cooling of a nanomechanical resonator. So that's this guy I was telling you about before. This is, we fabricate, what you see in the background is the capacitor of this Josephson cavity. If you look really closely over there, you can see the Josephson junctions themselves. And now the idea of this device is that if we put a magnetic field in plane, this beam actually closes the squid loop. It's a superconducting beam that closes the squid loop. And if he goes up or down, then it changes the magnetic flux. And since squids are sensitive to magnetic flux, that changes the frequency of our cavity. We call this flux-mediated optomechanics. Actually, if you want to know the details, these are not like the other junctions. These are actually sort of a funny little nano bridge junction. So there's some nano in the talk. Oh, I'm going the wrong way. Good. So, and this is the basic idea. You put a big field. If you could put a really big field, then the displacements of this beam up and down give you a change of the flux given by this, and you should get really strong coupling. You should get really big coupling between your mechanics and your microwave cavity. So this is actually the device I'll talk about today. This is our second generation device where we made even fancier junctions to get larger critical currents. And then, of course, you want to have a big in-plane field and a very small out-of-plane field, and you want to get it exactly tilted the right way. So we built our own 2-axis vector magnet that we put into our dilution fridge at the millikelvin plate and put 5 amps through it. It's kind of crazy, actually. But then we did these experiments. And now what I'm going to show you is we can tune that resonance with flux. So if we change the flux, the resonance frequency of my cavity tunes. And then I'm going to put this strong pump. So just like the previous section part of the talk, we're going to put this huge pump here. And what happens is that as my resonance tunes across the pump, then you get this splitting. As the resonance gets closer and closer to my pump, he starts to get oscillated by this pump field, and then he kind of shifts lower in frequency. And that, it turns out, was really useful because the resonance we have a lot of flux noise. This is the problem in these experiments. You also heard about flux noise the other day. It turns out that this pump can stabilize my resonance. It's like we have an internal feedback loop that locks the resonance of my cavity to my signal generator. And it does that because if he moves away in frequency, then his photon number goes down, so he goes back up. And if he moves closer in frequency, his photon number, the pump photon number goes up, and he gets pushed back down. So we get this huge, actually the main fuss about this whole thing is that actually we got a huge stabilization of our cavity from this pump. Now, the mechanics and the microwave cavity are coupled, and that allows us to cool. This is a picture from an optomechanics review paper. You do this just like you do laser cooling in atoms. You detune, you shine a laser on your cavity that's detuned by the mechanical frequency. And because of the cavity shape, you can only scatter up and not down. And each scattering up causes you to lose a phonon. And that allows you to sort of vacuum cleaner suck phonons out of your mechanical resonator and cool them in principle to the ground state. It turns out that, so what we did in this experiment is that we did a funny thing. Well, we didn't do this. We did the red sideband, it didn't work so well. And we fiddled around in the lab and we discovered that in this funny situation with this drive, we can put a tone on the blue sideband of this idler mode. And it turns out that we also cool. So we kind of have we put this pump on the wrong side. But using that, we could actually cool, we thought we had a chat once, and I got super excited in COVID in my bedroom because they told me they were in the ground state, and we calibrated it a little bit more, and it turns out we weren't anymore. You can get very close to the ground state. And it turns out that actually that's kind of, we understand that now. It took us a long time to understand this, but actually this idler mode, it turns out it's the equivalent of a negative mass oscillator. And negative mass oscillators have the phenomena that as you put excitations into them, they go down in energy. And that exactly reverses the role of these blue and red sidebands. Good. And no, then we also can put care, it turns out this care can also amplify. We're basically making a parametric amplifier. We did this again with photon pressure coupling device. We turned the cavity into not only a cavity, but an amplifier. You can see we now have gain on both the signal and idler modes. We get enhanced sensing. In a weird thing that we didn't understand, we actually get a larger coupling, like a larger vacuum coupling rate from something that somebody told me that's called Hamiltonian amplification. And what is very strange is that we tried this cooling gain now just on the red sideband. And there's a sort of general rule that the way cooling works is that you have a hot thing and a cold thing, and you couple them together, and hot flows from hot to cold. So you cool your lower frequency thingy. And it turns out that here so usually you're limited, you can't get colder than your hot thing. But it turns out in all of when we did the math and we calculated it out, we were cooling like a factor of 3 or a factor of 2 colder than our hot thing. And we were like, what is going on? And it turns out later we discovered that it's because with this amplification, this flow rates are actually not the same. So we actually have a non-reciprocal flow of heat quanta from one to the other. Good. So in summary, I've talked about strongly driven Josephson junction cavities. They're good for sensing. There are new weird modes that appear, which are both useful for enhanced sensing and cool physics. I would like to thank in particular Daniel and Ines, who have spearheaded this thing on their own really for 5 years. And also Fatime was instrumental in this initial understanding of these signal and idler resonance modes. And if it sounds interesting to you or someone you might know, we have positions open for PhDs and postdocs. So I encourage have them contact me. Thank you. What causes a limit of stabilization? At some point you hit sort of a, I don't think you can stabilize out the, say, intrinsic losses. So it's really, there's a good question what the band, I guess the bandwidth of the feedback is going to be comparable to the kappa. Right? So you can't lock out any noise that is faster than the kappa. So probably the intrinsic loss, which is very fast at the cavity frequency, you're not going to be able to get rid of. But it's very useful for getting rid of the stupid annoying flux noise, which is usually pretty slow. And I think that in terms of, we haven't gone through an analysis of how much of the flux noise was there and how much we locked out. But yeah, my guessing we're probably locking most of it out at the price, of course, to cavity field fluctuations of the probe, because that's where you pay a bit of price. And ultimately, there will probably be some noise that will come back in through the cavity the cavity field amplitude of the pump that will cause us trouble down the line. Yes.
Thank you for the talk. A lot of sharks, I like that. I have 2 questions. The first question was, you said that the probe does not see the shark, right?
Yes.
I would say that the probe sees still something different than if it would be a linear cavity. Did you see any signatures of that?
So no. So as far, I think from our experiments, they're Lorentzians, like one would expect. I think. Well, but okay, they did in the theory. So also in this paper, Daniel and Ines were very mathematically and algebraically inclined, have actually calculated out the response. And my understanding was that it's Lorentzian, but maybe it's definitely not Sharky at low power.
I probably agree with no shark. I'm just saying it's not a Lorentzian that I would.
Okay, that could be. That could easily be.
But it's a really slight difference, so it's easily taken for.
I see.
And the second question is about the you didn't have much time, right?
Sure.
But we have also looked into non-reciprocal cooling, right? That works, right?
Yeah.
But if you just have hopping, right, you're always limited. You can't cool colder than the bath you're coupling with, as it's normally the case.
Mm-hmm.
So can you reinterpret now the picture where you say you go below the temperature of your bath, you cool with an effective bath temperature that you actually lower the, so why does it work here?
Good question. I don't know offhand. There is a bit of a story that we're sidestepping here, which is that there's also part of the noise will be going into the idler mode as well. And so the fact that our radio frequency mode looks hot, I mean, so you might ask, so why, if you look at this carefully, it looks like I told you at the beginning it should be in this ground state, but now it's getting hot. Where is it getting hot from? Here it's getting hot actually because we are amplifying the quantum noise. So we have gain in the cavity, we're amplifying the quantum noise. And I told Daniel in this, but amplified quantum noise is not heat because it's still a pure state. But I think the answer is that this is because when we amplify the quantum noise of the signal mode, it's not really amplified noise, it's 2-mode squeeze with idler mode. So I think that in the end, probably it's a little bit more complicated, but we should talk.
Okay, more. Let me ask a very naive question. I'm
Perfect.
biophysics. So when you showed this diagram of power versus the number of photons, there was obviously this gap. And
Oh,
so in the early part, yeah.
probably there.
Here,
Yeah.
So if is that something like a band gap? Because if I go from left to right, there's a huge jump.
Yeah.
And how do you get these photons in so suddenly?
So this is a very difficult experiment because as we pump all of the, this is sort of I think maybe the best way to say it is this is sort of the metastable bit of that Duffing curve. And what actually happens, well, let's say I could say very experimentally, what happens is that as we go, experimentally, we turn up the power, right? But the power is not directly proportional to photon number because we have to calibrate it out. But as we turn up the power, then we see the signatures of this idler mode. And this is here where the cavity bifurcates. And it jumps from one amplitude of the pump to the other. And so this is sort of an inaccessible experimental regime for us.
Can I think of it as like a bunch of photons that are jumping in?
Yeah, well, let's say the way you should think about it is that, if you have a Duffing oscillator, my speaker, and he's just on this lower branch, and I'm pushing him with my finger, and sometimes he'll just suddenly jump. And then when I push, he'll jump up, and then suddenly my finger pushing with the same force will give me a much bigger amplitude.